Dear students, welcome to 29th online class of Control System Engineering. In last class we studied how we can improve the transient state specification and steady state error specification independently for a system. And for this we designed a proportional integral derivative control or a PID controller for a system. This PID controller is made up of active components. Dear students, after this lecture, you will be able to design a compensator to improve both steady state error and transient response of a closed loop system. Dear students, contents of this lecture are design of lead lag compensator for a closed loop system. Dear students, in previous example, we serially combined the concept of ideal derivative and ideal integral compensation to reach the design of PID controller, which improves both transient response and steady state error specifications. Now we will study how to improve both transient response and steady state error by using a lead compensator and lag compensator rather than the ideal PID. Our compensator is known as lead lag compensator. We will first design a lead compensator to improve the transient response. Next, we will evaluate the improvement in steady state error still required, and then we will finally design a lag compensator to meet the steady state error requirements. Dear students, the following steps summarize the design procedure of lead lag compensator. At first, we will evaluate the performance of uncompensated system to determine how much improvement in the transient response is required. After this, we will design a lead compensator to meet the transient response specification. And the design includes zero location, pole location, and the loop gain. Then we will simulate the system to be sure that all requirements have been met. We will redesign the simulations if required. We will evaluate the steady state error performance for lead compensator system to determine how much more improvement in the steady state error is required. After this, we will design the lag compensator for improvement in the steady state error. Then we will simulate to make sure that all requirements have been met. And we will redesign if required. Dear students, in the given example, we will design a lead lag compensator for the system so that system will operate at 20% overshoot and will have two-fold reduction in the settling time. Further, the compensated system will exhibit a 10-fold improvement in the steady state error for a ramp input. Students, if you look at forward power transfer function of the closed loop system, in this we have three poles. One is at origin, second at -6, and last pole at -10. We will start a solution by sketching a root locus for the system. And then for overshoot of 20%, we will find the value of damping ratio zeta, which equals 0.456. And corresponding to this, we will draw a radial line in S plane with the angle of 117.13 degrees, which is shown in the figure. Now, the desired point where system will have 20% overshoot will be the point where root locus will intersect the radial line, and that is minus 1.794 plus minus j 3.501 with a gain of 192.1. Dear students, now in order to have twofold reduction in the settling time, the real part of dominant poles of uncompensated system must be increased by a factor of 2, because settling time is inversely proportional to the real part of dominant pole's location. So here, by multiplying the dominant pole's real part by 2, we will ultimately divide settling time by 2. So for a new design point, the real part of dominant pair of pole will be equal to 2 times the real part of dominant pole of uncompensated system, which give us the value of minus 3.588. Now we know that the compensated system will also have overshoot of 20%, so the new design point will also lie on the line of constant damping ratio. Now making a triangle and using trigonometry, we will find the imaginary part of new design point, which is equal to 3.588 multiplied by tangent of 117.13 degrees, and this will be equal to 7.003. Now if you look at root locus in previous slide, you will observe that the new design point, which is minus 3.588 plus minus j 7.003, is not the part of root locus. And to achieve this specification, root locus must pass through this desired point. Now for this, we will reshape the root locus with the help of lead compensator. For this, we select the location of compensator 0, coincident with the open loop pole at minus 6. Choosing this location will eliminate a 0 because a pole 0 cancellation will occur, and the lead compensated system will be left with 3 poles only, the same number of poles that uncompensated system has. Dear students, from the root locus, now we will find the angles of all the poles and zeros of uncompensated system and 0 placed by a lead compensated system to the new design point, and then we will sum all these angles of uncompensated system poles and zeros and compensated 0, and will get the result of minus 164.65 degrees, and we will calculate its difference with 180 degree by using the relation that sum of angles of zeros minus sum of angles of poles is equal to odd multiple of 180 degree, because this criteria must be fulfilled to include this point into the root locus. Now the angular contribution required from compensator pole is equal to 15.35 degrees. Now using the geometry from the figure, we will calculate the pole's location. From this, the location of compensator pole is found to be minus 29.1, and we will again calculate the gain with compensator pole and zeros and uncompensated system poles, and it is found to be equal of 1977. Now after designing a lead controller, we will start lag controller design. Since the uncompensated system transfer function is given by g of s equal 192.1 divided by s into s plus 6 into s plus 10. Here gain k is equal to 192.1 for system operating at 20% overshoot. Dear students, now we will calculate static error constant for uncompensated system. The static error constant is inversely proportional to steady state error is equal to 3.201, where the steady state error is 0.312 for the uncompensated system, where the design problem requires 10 times reduction in the steady state error. The required steady state error will be 0.03122, which is 10 times less than the steady state error of uncompensated system. Now the static error constant associated with this steady state error is 32.051. Students, the figure represent root locus for the lead compensated system. Dear students, the open loop transfer function of lead compensated system is given by 1977 divided by s into s plus 10 into s plus 29.1. The static error constant associated with lead compensated system will be 6.794, and the steady state error will be 0.147, which shows that lead compensator has improved the steady state error of the uncompensated system, and this improvement is a factor of 2.122. Since the requirements of the problem specified a tenfold improvement, so the lag controller must be designed to improve the steady state error by the factor of 4.713, which is calculated from 10 divided by 2.122 equals 4.713 over the lead compensated system. In lag controller, we add a compensator pole and 0. Pole is near to the origin and 0 is near to the compensator pole. And the ratio of compensator 0 to compensator pole is equal to the ratio of static error constant of required error to the static error constant of lead compensated error, and this will be equal to 32.05051 divided by 6.794, and will be equal to 4.71. Dear students, after obtaining the lag compensator 0 to pole ratio, we will arbitrarily choose at minus 0.01, which places the lag compensator 0 at 0.0471. And the lag compensator transfer function is given here. The lag lead compensated system open loop transfer function is also given here. Dear students, the figure represents root locus for lead lag compensated system, where uncompensated system pole is cancelled by a lead compensated 0 at -6. Now along the root locus, search the point where root locus intersect line of constant damping ratio, and that is our desired dominant pole location, and the location is -3.574 plus minus j 6.976 with a gain of 1971. Dear students, the table summarizes system response for compensated, lead compensated, and lag lead compensated system. It also shows the position of dominant poles, gain, transient specification, and steady state error. Dear students, Figure 1 represents step response of compensated and uncompensated system. You will observe a clear difference in the speed of the response. In figure 2a, we have system response for ramp input for uncompensated and lead compensated one, where the figure 2b represent ramp input response for lag lead compensated system. Now if any of you have any questions, please ask.